Sorry guys, I'm a little bit slow on the draw here. Let me hide this so that we can get started. We're going to be looking at the next unit in our series on quadratic functions. This is unit 2 from chapters 3 and 4 with the quadratic functions. And today we're starting the section 4.1 where we're going to take a look at solving quadratic equations by graphing. So the objective of this video is to simply, as we said in the title, solve quadratic equations by graphing. Take a look at the vocabulary words and make sure you watch for roots, zeros, quadratic equations, quadratic functions. Make sure that these words become something that you're comfortable with as you listen. Now, as you know, we've been learning about different versions of the quadratic function, the standard form, the vertex form, and within those, we have talked about how do we find the various parts of the graph or the function? How do I find the vertex or the axis of symmetry? How do I know which way the graph opens or the y-intercepts or whether it's got a maximum or a minimum or what its domain and range might be? These have all been parts of our topic so far, but there's been one thing that we've been avoiding, and that is the x-intercept. So how do we find the x-intercepts? Well, it turns out we're going to be taking the rest of chapter 4 to kind of talk about how do we find those. The first one we're going to do is simply by looking at the graphs. And so we will be using our graphing calculators to be able to do that. Now, first, a couple of words that I want to have so that we can be sure to be clear on the language that we use. When we're solving a quadratic function, a function refers to the quadratic that is equal to f of x or y. And then what's happening here is that we are putting in values of x, they come out as a y, and we take those ordered pairs and draw a parabola as we go along. Well, if we're solving a quadratic function, we're going to stick to something that makes sense in terms of the graph itself. We're looking for the x-intercepts or the zeros. Whereas if we go to a quadratic equation, a quadratic that's equal to something, we will use the word roots. We're looking for the roots. Now, make no mistake, though, these are the same things. We are still looking for the same things. It's more the language that I want you to watch for so that when you see it in the instructions, you're not confused. Why are they asking me for roots now and x-intercepts here and zeros there and solving there? It's all part of the same picture. Okay. So taking a look at this one, if I said to you, okay, find the roots of this equation and do it by graphing. You draw a graph. You'd look for the place where this particular parabola touches the x-axis. Looks like it's just at one spot where an x is equal to a 4. So the root of the equation is a 4. If we were going to look at something that involved a fountain, the jets of water in a fountain are designed to land precisely on the underwater spotlights. If you could represent the curve of the water by this quadratic function, where h is the height of the water and x is the horizontal distance, how far from the nozzle should the underwater lights be placed? So we graph it. We take a look. Here's our jet of water coming up, and it lands again here at 2. And if we look back to make sure we understand what the units were, they were meters. That means we're looking to place our underwater spotlights at 2 meters away from the nozzle. If we had, we're looking at the water pressure, for instance. Suppose the first function below represents the path of a jet of water at maximum pressure, and the second one is at a lower pressure. So graph the two on the same graph and compare them. So you can see the first one going higher and further, and the other one is going much lower, stopping a lot shorter. Lastly, we have one where we're looking at the curve of a suspension bridge cable, which is attached at the top of 2 towers. And they established that the height right here is the distance from the top of the tower. So if we were to go, this is the top of the tower, so the height is nowhere, like that's 0. And if we're dropping down, that's how far down it's going. So if we were to graph this and figure out what the distance was, we would have it bopping down here. We'd want to know the distance between this vertex and that vertex. So there you have it. You're going to need to use a graphing calculator. You can try using Desmos if you don't own your own graphing calculator for these questions. And if you don't have access to regular internet, please don't worry about it. Just look at the solutions at the back of your textbook and just practice looking in the right place on the graph for the question that you're answering. So a very straightforward section, solving quadratic equations by graphing. As always, make sure you take a look at each one of these questions. And if something seems unclear or confusing, that you seek out answers for it somewhere. Come and talk to me, and I'd be glad to help you. Okay, take care, guys.